Good morning to one and all. I am Keshav Pandey and I am going to speak on the topic the applications of automata in game theory. So, we'll start with the introduction. Any problem with interacted participants and actions can be treated as a game. When car drivers put a plan to drive in heavy traffic, they are actually playing a driving game. Game theory is a mathematical tool that can analyze the interactions between individuals strategically. The interactions between agents who may be individuals, groups, firms are interdependent. Now we will talk about automata types. An automaton is a self-operating machine. The output of one automaton is a combination of sequences of the current input and the history of the machine's previous input. An automaton is designed to automatically follow a predetermined sequence of operations or respond to encoded instructions. There are many types of well-known automata, such as finite automata, Turing machines, push-down automata, and adaptive automata, as well as other variations such as random access machines, parallel random access machines, and arrays automata. Now, we will talk about learning automata theory. Learning is strongly associated with past experiences, where these experiences are meant to permanently change the entity behavior. A learning automaton operates in a random environment. The actions are chosen based on the inputs received from the environment to find the optimal. The learning schemes came in two structures: fixed structure and variable structure. Here we are seeing the concept of automata. Now we will talk about finite state automata. Finite automata is one of the well-studied computation models in theoretical computer science. Finite automata are composed of fixed finite memory which takes its decision using that finite memory, a finite non-empty alphabet, a transition function, an initial state, and a set of final states. Transitions map ordered pairs specifying the current state and the current input symbols into a new state. Finite automata are classified into deterministic finite automata and non-deterministic finite automata. DFA is only permitted to be in any one state in any time. On the contrast, NFA can be in two or more states at any given time. Technically, adding restrictions to DFA is sufficient to transform it to NFA. However, there are two types of transitions from state A to state B, that is transitions with an input symbol R and empty transitions A and alpha, and empty transitions A alpha which do not modify the input. DFA can be viewed in two schemes: graph-based, graph-based and table-based transition listing schemes. Graph-based scheme is considered efficient for visually representing players' behavior, while table-based transitional listing scheme is efficient for computer simulation. Mathematically, finite automata are four-tuple structures described by R as follows. We can see here the figure of input and empty transmissions from A to B. R equal to S, I, F and S naught, where S is a set of states, I is an input symbol, F is such that S cross I gives S is a transition function, S naught belongs to S is an initial state. This definition induces the concept of current state for a given input sequence. That is, given a sequence of inputs I star is equal to I1, I2 IT, that belongs to IT. The current state ST is defined recursively for t bigger than 0 as ST equal to t into ST minus 1, comma IT, together with the initial state S0. Adaptive automata. Many studies have been conducted in the field of adaptive and learning systems. The attention on such studies comes from the suitability of those systems in modeling many real-world complex systems. In typical learning automata systems, a self-operating machine responds to a sequence of actions to achieve a specific goal. The automata, in turn, may respond based on predetermined rules, or it may adapt to its environmental dynamics. In other words, adaptive actions are attached to the state transition rules of the adaptive automata, and they are activated whenever the transition is applied by removing or inserting new elements to the automata's transition set. Mathematically, adaptive automata can be defined as a 10-tuple R as follows: R equal to S alpha I naught F sigma U dot H Q delta, where the tuples of R are classified as into the following categories. State tuples. This category includes tuples S I naught and F such that S is a set of states. I naught is initial state of the automata. F is the final state. Input tuples. This category includes tuples alpha and this such that it's a set of input symbols. Now, transition tuples. This category includes tuples sigma and u, h, q, and delta, such that sigma is the transition relation where this relation takes two elements, an element from u and a set of mapped parameters from q. U is a set of adaptive function labels. H is a set of generators. Q is used for mapping parameters, variables, and generators to u. Delta is a set of adaptive actions, plus, minus, etc. arithmetic. Now we will talk about cellular automata. The structure of cellular automata is based on lattice of cells, where each cell may be in a predetermined number of discrete states. Updating the states of CA in each time step requires a predetermination process of the neighborhood relation, indicating the communication structure between the cells. We can see here in the figure of adaptive automata. For simplicity, the following are the basic properties and characteristics of a given CA. The cells are regularly arranged in an n-dimensional grid. Each cell has an initial state selected from a finite set of states. Update is carried out in a discrete time step. Changing the state of the cells depends on the set of local rules. The selected transition rule is applied to all cells. The update process is carried out simultaneously for all cells. Mathematically, a cellular automata is defined as a full tuple R, where we can see R is equal to N S P F, where N is the dimension of lattice space, S is a finite set of states, P is a finite set of neighborhoods, F is the local rule of CA. However, cellular automata are considered easy to implement and emulate on a computer. And in addition, cellular automata exhibits a wide range of possible non-linear behavior and thus can produce output at the highest complexity level of formal language theory. The applications of automata in game theory. So we come to the main topic here. The automata theory has presented various types of automata with different characteristics. In this section, we will go through the applications which have successfully utilized the concept of automata in game theory. Applications of finite automata. Back to 1985, Neyman tries to model the fact that players can do only bounded computation by modeling the iterate prisoner's dilemma players as finite automata. 1 year later, Robinson tries to show that costly computation may affect on an agent's utility. Robinson assumed that players choose a finite automata to play the game instead of choosing a strategy directly. It was clearly stated that a player's utility depends on the automata's moves and the complexity of the automata structure. On the other hand, there is a difference between the environments for representation the players in lattices, trees or graphs using EA's techniques based on many factors that in turn affect back the outcome of the evaluation of strategies. Some of these factors include the number of players, technique of evolutionary computation, type of automata, and neighborhood structures. In the here, the authors have reported that they built their three prayers model using a genetic programming technique to discover high quality negotiation policies, where the behavior of the players was represented by finite automata. Now, we will talk about applications of adaptive automata. Adaptive automata-based devices have been presented as powerful tools for defining complex languages. Adaptive automata have the following important features. The accepting procedure performed by an adaptive automata is done efficiently due to its structure, which is based on finite state or structured pushdown automata. Adaptive automata can handle context dependencies in a strict synaptical way without the aid of auxiliary semantic procedures. The structure of adaptive automata can be extended to implement transducers, allowing the generation of parsed trees as a side effect of parsing sentences. Generally, adaptive automata have cheaper implementations compared to other mechanisms. Adaptive automata can be considered an alternative to existing natural language processing solutions. In order for adaptive automata to do self-modification, adaptive acts adhere to the state transition rules and are activated whenever the transition is used. The adaptive mechanism can be defined as adaptive actions that change the behavior of adaptive automata by modifying the rules defining it. A simple notation for representing adaptive automata should have some features such as being at least compact, simple, expressive, unambiguous, readable, and easy to learn, understand, and maintain. However, finite automata are a particular case of adaptive automata. The model can be reduced to finite automata if the automata have no rules associating adaptive functions to transitions. This characteristic is considered important to use adaptive automata naturally, where finite automata are required. Now, applications of cellular automata. Cellular automata can be complex systems by themselves, or they can offer good ways of studying the behavior of complex systems. In this section, we overview the existing models and algorithms that have successfully utilized cellular automata to analyze or achieve desired dynamics of a complex system. The presented work uh, has modeled the participated agents in a given game as stochastic learning cellular automata. Stochastic learning means that behavior is not determined if it is shaped by its consequences. In the same context, other works have modeled the agents differently, such as modeling agents as a combination of cellular automata and as stochastic learning automata. Recently, cellular automata have been used to simulate agents with different strategies. In that work, the researchers showed the ability of co-evolutionary learning used to evolve cooperative strategies in structured populations. Using the n-player iterative prisoner's dilemma, that is called NIPD in short. In addition, they examined the effects of both fixed and random neighborhood structures on the evolution of cooperative behavior in a lattice-based NIPD model. Kenameth et al. Has presented a model to simulate and solve complex systems. The model is based on cellular automata with some approaches for agent programming, such as artificial intelligence, automotive modeling, distributed computing, swarm intelligence, and genetic algorithms. We can conclude that representing the behavior of n players prisoner's dilemma models using cellular automata has a great benefit since most of the researchers can utilize it to distinguish the effects of neighborhood structure on the evaluation of cooperative behavior. Now, in conclusion, I would like to say that presenting players' strategies in game theory is one of the factors which affect the player's performance significantly. In this work, we have analyzed the characteristics and the underlying structure of existing types of automata. Consequently, we have explored the applications of automata in game theory. However, this study revealed that only a few types of automata have been utilized in game theory. We found that finite automata have been widely used to represent simple agents' behavior. On the other hand, adaptive automata and cellular automata are mainly used to represent complex agents' behavior. The complexity level of both adaptive automata and cellular automata is determined by the number of states in the automata. The more states we have, the higher has the capability of those automata to handle complex strategies. I have taken references from the following articles. Thank you, ma'am.